Okay, chapter 3 and 4 practice test. This is one version of the practice test from the chapter 3 and 4. Printed as ID 2. I don't know. We'll see if that... whatever. Anyway, so this is one of those variations. Hopefully you can still find a PDF of this or whatever. I'll plan to have that on there. Anyway, x to the 3 minus x squared minus 4. We're supposed to graph it. You can do this different ways. You can start looking for zeros of the function or whatever, intercepts, you know. But I think that in this particular case, maybe we'll just try it the old-fashioned way. 0, 1, 2, 3, negative 1, negative 2, negative 3. And you can go into like 4 and 5 and stuff too, as you see fit. And so we just try stuff. If I plugged in a 0 there, 0 to the third is 0. 0 squared is 0. Minus 4, so this is negative 4. So we start out at negative 4. 0 over is the x and negative 4 is the y. There's our first dot. After that, if I plug in a 1, let's see here. That would go something like here. I'll do it on the side. That's 1 to the third minus 1 squared minus 4. That's 1 minus 1 minus 4. That's just, whoa, that's also negative 4 because 1 minus 1 is 0 minus 4. So this 1 also is at negative 4. Freaky. And then let's see how this goes. Okay, so if I plug in a 2, we'll put an equal sign there. If I put in a 2, 2 to the third minus 2 squared, put little parentheses on it, minus 4. Let's see. This is 8 minus 4. And then that's 4. Take away 4 is 0. So we plugged in a 2 and we got out a 0. So then if I plug in a 2, I get out a 0. That means I'm up here. And then we have a 3. If I plug in a 3, let's see here. 3 to the third, 3 squared. Oops. Don't tell anybody. 3 to the 3, 3 to the 2, minus 4. That's 27. Take away 9 is 18. Minus 4 is 14. So that one's skyrocketing way up there by then. By the time I plug in a 3, it's way up at 14, way beyond the graph here. Something up there. But that indicates to us that what's going on here is some sort of a turn or something. I don't know if it dips down much or if it's just going straight across. But from here to there, it seems like it's going upstairs. Because by the time we get to that 3, it's way up yonder. Something like this is going on. And then we'll just try things to the left. Negative 1, negative 2, negative 3 in the same way. And it'll do something. I'm betting because of the nature of this being x to the 3 thing, it's probably going downstairs. But it might loop back up a little bit before it does. So make sure you try those dots. Anyway, so that's how that goes. If you plug in it, here I'll do one of them for you just to remind you about how negatives go. If we plugged in a negative 1 to the third, I keep writing 2. Negative 1 to the third minus negative 1 squared minus 4. Negative 1 to the 3 is negative 1. Negative 1 squared is positive 1. But I am minusing it. So this is negative 1 minus a regular 1. And feel free to write that out more if you like. That's negative 1 minus a regular 1. And then minus 4. And so if I were to do that, negative 1 minus regular 1, that's negative 2. Negative 1 minus 1 is negative 2 minus 4 is a negative 6. And so if I put in a negative 1, we got ourselves a negative 6 out of it. Negative 1 puts us down at negative 6. Looks like by the time I get to 1, negative, this thing's already downstairs, so it's probably just taking a downturn. Some kind of a smooth transition here is what I'm betting. You know, you can always get more detail if you want to plug in more dots. Anyway, that's what I'm seeing here, something like that. Probably not going up like this. Okay. For the second one, we'll go ahead and sketch a graph at some point, but we're determining the real zeros here and stating the multiplicity of any repeated zeros. And so remember how this goes. This one is fortunate for us because it's small numbers, you know. But the way it would essentially go is, guys, we're going to say I have to determine the numbers that will, if I plug it in, if I plug some number in everywhere I see an x, what makes this function end up equaling 0? Or in other words, it's like it's the x-intercepts in graphing terms, you know. I just want to make this y part equal 0, and I don't know what does that. And so I got to figure out that. But remember, by the rational root theorem, we can look at the very last number and the very first number that's with your x to the third part. They're both 1s in this case. It's a negative 1, but that won't matter. And so we'll say rational root theorem says that if I'm going to find some decent zeros here, that are not all funky, imaginary, weird stuff or anything, they will be of the form of things that go into 1, which is fortunate for us only 1, over things that go into this number, which is also 1, which is great for us because it's not much to try. And there's a positive and negative. Oh, that's not a negative. A positive and a negative version of this. And so essentially, guys, 1 over 1 is the only variation we got because it's not like there's a list of a bunch of things that go into 1 here. 1 over 1, so I will try 1, and I will try also a minus version of that. And we'll see if one of those gives us the first 0 that we can find, or a rational 0 we call it. Hopefully we can get 1 out of that. And remember, you can do that by plugging these numbers in. When it's small numbers like 1, it's pretty easy to plug them in. In case you get bigger numbers and stuff to try on your test, maybe we'll try and suggest doing this by synthetic division. That tends to work faster. So I'll plug in a 1 here, and let's see how that goes. Oh yeah, I said I'd do it by synthetic. And so this is a -1, -1, 1, 1. -1, -1, 1, 1. And then we'll try and plug this junk in. If we do a 1 there, by synthetic division, -1 drops down. 1 times that -1 is -1. These things add up to -2. Timesing that -2 with the 1 is -2 again. 1 plus -2 is -1. And -1 times that 1, -1 times that 1, will be -1, plus the 1 up here is 0. We got ourselves a 0 remainder, which is equivalent to us having gotten a 0 when we plug it into the function. That's good for us. So that means the number that we tried here, this 1 here, that's one of our zeros, so positive 1. So we'll keep that in mind. So 1 is one of our zeros, positive 1 is one of them. And, you know, you could put x equals 1 or something like that. And then what's left over here, guys, is, now remember, this was an x to the 3 equation. And what we divided out was essentially the equivalent of an x minus 1 factor. But whatever, it's essentially going to knock us down 1 power of x like we do when we're doing synthetic division. And so then this remaining function here of what's left over after I get that 1, 0 is, we'll say, this is a -1x squared and a minus 2x and then a minus 1. And now we just have to figure out what makes that thing equal 0, you know? And that might not be super obvious. Maybe you got to do quadratic formula if it gets ugly, but we got to solve it out just to get this thing equal to 0 like the old-fashioned days. I don't like having a negative in front of my x squared, so it's okay if you guys like to do this too. You can times both sides by a negative. I'm timesing by a -1, and what that does is it'll clean up the negatives for me, so it's a regular x squared, and a positive 2x, and a positive 1, and 0 times anything is still 0, and this will work out well. And from there, we just got to figure out what are the numbers that times to 1 that add up to 2. And there's no negatives anymore, so it's not that bad. 1 times 1 makes 1. And those same numbers add up to 2. So then once we're there, we'll just say, well, I'll solve these things both out for 0, figuring out, well, what's the new 0 here? -1 plus 1 is 0, so -1 there. And this is the same thing, so -1 plus 1 makes 0 here, and we have 2 of that. So they ask you, what are the zeros of this? What we got was, first off, we got a positive 1 out of it. Then we got a -1 twice. And so the way we would say that is we'd say, well, positive 1 is one of the zeros, and we can draw that in here into the graph. And then -1 is 2 of them, so we say it's positive 1 is one of the zeros, and then this one, -1, has what we call a multiplicity. You can just abbreviate a multiplicity of 2 because there's 2 of them, you know. That's what we mean is you see multiplicity of 2, it just means that we have 2 of the same thing. But it has implications for our graph as well. So let's see here. If I have, first of my zeros is at 1, that means I go to positive 1, and that's where it's essentially an x-intercept there. I hit the x-axis, and it'll go through. I don't know if it's going downhill or uphill, but at some point our function is going to pass through that dot. And then at -1, we have a multiplicity of 2, and what that tends to look like, guys, is if you get multiplicity like that, it means that you're not typically like running through the function, or sorry, through the x-axis. You're actually just going to graze past it, so either coming from below it and then just hitting it and then going back down maybe, or you could be coming from above it and then graze it and then go back up, but you're not passing through. It's not like that. So if you get a single root or a single zero, you're passing through. When you get multiplicity, a couple of them like that, it's probably just dipping down and coming back up, or the other way around. It's not crossing. And that's the same thing of multiplicity 3 and 4 as well, if I remember right. And then let's see here. From here we have pretty much the zeros figured out, and we mentioned the multiplicity. We don't have a real good picture of the graph. All we know is that it passes through the x-line here, and that it grazes the x-line here. And so beyond that, we'd be guessing. This is a negative x to the 3 thing. If I were to guess, I'm betting that it goes downhill, up for a little while, it grazes past it, and then down back through. But again, if you're, you got test points riding on this, so if you're wanting to be super careful and you're not sure if there's 2 different graphs that look similar, feel free, because we might be looking at multiple choice or something on the test. If you want to get better detail than this, you can always just start plugging in more numbers too. You can plug in 0 to see where the y-intercept is, or you can plug in 2 and 3 and 4 and negative 2, 3, 4, and then we'll get a better picture of what this all looks like. But I'm betting that it looks something like this. Okay, what else? Number 3. We got to find the x-intercepts where the graph crosses the x-axis and those where it does not cross, and then sketch it. This is the same kind of thing. And so I'm not going to do the whole thing with you, but I will at least get us started, because all the ones in that last one kind of made it a little bit messy. But when we say x-intercepts where it crosses, remember, that's where we don't have multiplicity greater than 1, and those where it does not cross the x-axis, those are just if you get a 0, if you happen to get a 0 where it's, if it has a multiplicity of 2 or more or something like that, if you get 2 of the same number that's making zeros here, then you would say, well, that's a place where I don't cross it. I just graze past it like we were saying on the last problem. I'll let you guys work those details, but to get this thing started with finding the first 0, since this one has more interesting numbers than the last, we could say I need to guess numbers that come of the form of things that go into 8 on the top. So plus and minus things that go into 8, that's like 1 goes in, 2 goes in, 4, and 8 goes into 8. Over things that go into this first number here, which is again a 1. And so then that's going to be, I guess, only 1 goes into 1. And so then that's fortunate for us too, because then if it was like a bunch of numbers down here, you have all these different variations of what to try. It's a little bit easier. There's no fractions, because it's either going to be a 1, positive 1 over 1, or a negative 1 over 1, or a positive 2, or negative 2 over 1, or 4, or 8, 2, negative 2, 4, negative 4, 8, negative 8, ... And you don't have to try all these. Remember, we're just going to try one at a time, hoping to get a 0 until one of them works. And then we'll reduce this down to a quadratic x-squared looking equation, and then solve that easier. So let's just try one of them real quick. If we do one of them by synthetic division, this is a negative 1, negative 6, negative 12, negative 8. Negative 1, negative 6, negative 12, negative 8. Little synthetic division going on. Let's see. If we try, now you don't have to start with 1. I like to start with small numbers. That's why I'd start over here. But if you have some feeling about another one of them working, then try it. I'm going to start with positive 1. Dropping that down, let's see here. Negative 1 drops, and then we have 1 times negative 1 is negative 1. These add up to be a negative 7. Negative 6 and negative 1 make negative 7. Then timesing this, that's negative 7. Then add that up. What is that, negative 19 or something? Times 1 is negative 19 still. This does not make 0, because these won't add up to 0. Not going to work, Shoot, that's like negative 27 or something. It doesn't matter. It's not 0. So that didn't work. So 1 didn't work. And then you can rewrite the problem, or if you feel like you got the room, or if you're not messy or something, you can make it work by other means. I'm going to try and squeeze a negative 1 in here and see if we can make that work. Dropping this one, negative 1 drops down. Negative 1 times negative 1 is positive 1. And then, let's see here, negative 6 plus 1 is negative 5. Times that by negative 1, we got ourselves a positive 5. It's going to get messy to do more than this. But anyway, it's positive 5. Negative 12 plus 5 is negative 7. Negative 1 times that negative 7 is positive 7. Ooh, so close. Negative 8 plus 7 is not 0. It's negative 1, so that didn't work out either. Ooh, let's see if we can get one of the 2's to work. Okay, if I did positive 2 dividing in there, negative 1, negative 6, negative 12, negative 8. Okay, negative 1 dropping down, that's negative 1. 2 times that is negative 2. Adding that down is negative 8. 2 times that negative 8 is negative 16. Adding that up, shoot, what's that? 28, negative, and then 2 times negative 28, this isn't going to work out, negative 56. These are not going to add up to 0. Let's try negative 2. Okay, drop in the negative 1. Negative 2 times negative 1 is positive 2. Negative 6 plus 2 is negative 4. Negative 2 times that negative 4 is a negative times a negative, so that's positive 8. Pretend like you can read that. That's positive 8. Negative 12 plus 8 positive, that's going to be negative 4. And this might work. So we have negative 2 times negative 4 is positive 8. Look at that. Negative 8 plus 8 is 0. This is good for us. Okay. Negative 2 works. And then what we got left over is the x squareds. Remember, it was x to the 3 before. Where'd that go? It was x to the 3 before. Now it's an x to the 2 equation after I divided that first deal out. And so, let's see here. This stands for negative 1x squared, or minus x squared, minus 4x minus 4 equals 0. Again, if you don't like negatives on your x squared, like me, you can divide or times by a negative on both sides. Then you're just dealing with x squared plus 4x plus 4 equals 0. And from there, you got options. You gotta, if this thing factors, then you can find yourself some really nice rational real numbers. It looks like a couple of 2's in there will work, If you get to one that doesn't factor ever, remember, you can always do it by quadratic formula as well. We might encounter that in a few minutes here. Anyway, so that's going on. You find a couple of zeros and etc. Then draw a picture of it best you can, much like the last one. Okay, number 4. Let's see here, number 4. Describe the end behavior of a function. So the end behavior, remember, that means we're going to try and discuss what happens as x values go out to positive infinity, and what happens as x goes out to negative infinity. This particular test generator or worksheet generator or whatever, they discuss this stuff in terms of limits, as we should. So they'll be mentioning the limit thing, and so you might see something like LIM written on top of your stuff. It's whatever. It just means everything we've been talking about. As you approach infinity, as you approach minus infinity, what happens? And we will describe that the function f of x is going to be approaching. And they'll do some limit thing for that too. The limit is as x approaches this, or blah, blah, blah. Anyway, so the function will be approaching either positives or negatives. And again, remember how this goes. All of these terms that are down here that have smaller powers than the third power guy, they ain't going to make much difference when you get out to a billion. So then we'll just say, well, okay, let's try what happens when I just look at this. If I plug in positive numbers here, a positive number to the third is a positive times a positive times a positive, no matter how big or small. So then if I get out to a billion here, or approaching infinity, this is a positive times positive is a positive number. So my function is going positive, and so we'll just say that's approaching infinity positive as well. And then limit as it approaches, as x goes out to the left or out to negative infinity, that's going to be a negative times negative times negative. Negative number to the third power, that's a negative times a negative is a positive. They cancel out. And then another negative, so that becomes negative. So in this case, the function will be approaching negative infinity itself. And then it's the same kind of situation on number 5. You just have to figure out what happens when you plug in positives and what happens when you plug in negatives. Don't worry about the smaller terms. That's kind of how number 5 goes. Number 6, we have 6, 7, and 8 are all long division problems. On number 6 and 7, you might notice you can do, well, at least on number 6, you can get away with synthetic division. So if you prefer, you can do synthetic division. Just remember, x minus 4 translates into a positive 4. And then we'll copy the old coefficients here. We got 2, minus 9, 2, positive 14, boom. And then throwing these things down like we do, like we've been doing, that's 2, and it's blah, blah, blah. Just like we've been doing. We already been using this technique, Anyway, but 4 times 2 is 8. That's like negative 1 or something. 4 times negative 1 is 4. Negative. And then that adds up to negative 2. And then 4 times negative 2 is negative 8. Positive 6 is the remainder. And so then the way you would say that, guys, is again, this was x to the 3. We chopped it down by an x, so now we're down to x to the 2. So this is a 2x squared, 2x to the 2, minus 1x, and then minus 2, and then anything else is the remainder. And there's different ways of writing remainder. You can just write remainder 6, Or else a classic way to do it would be to say the 6 is the leftovers that's over whatever we were dividing by, or 6 over that x minus 4. Either way, the 6 is the remainder though, and this is the quotient. Looking pretty good. Quotient and then remainder 6. Cool. Now over yonder on number 7 and 8, these are long division problems, and so I can't do it necessarily by synthetic division because the divisor is a little bit more complicated, especially in like number 8, and it's a nasty old mess. And so I'll probably demonstrate number 8 to you guys because it's worse looking. And so let's see how that goes. If we did, let's see here. I'm going to pause this for a second. I got to get a paper. Unpause. And that was like 75 years later. We're going to try and, here, we'll do this by long division. But that's a big old mess. And so check this out. Okay, 2x squared, 5x minus 1, that's the outside part. And so we'll just shove it on the outside. 2x squared, it's here. 2x squared plus 5x minus 1 on the outside, and then on the inside's the rest. What was it? Where to go? That's 6, 21, 8, minus 13, minus 4. 6, 28, 13, 4. Okay, we have 6, 21, 8, 13, 4. These are the minuses. That's an x squared, and x to the 3, and x to the 4. Pluses and all that. Make sure I didn't mess anything up. It looks like I copied it right. So that's good for us. Now we'll just do what we do. And so I have to divide first bit into first bit. 2x squared into 6x4. 2 into 6 goes 3 times. A lot of the time you'll have just no number here and just consider it a 1 like we do. Anyway, 2 goes into 6 3 times. X to the 2, I need 2 more x's to make 4 of them. And so then 3 times 2 is 6, 6, and then x2 and 2 more x's is 4 x's. That's good, but then we're distributing this, so then 3 times that 5 is 15, x to the 3. 15, x3, and then 3 times minus 1 would be negative 3, x to the 2, because there was 2 x's and no more x